This paper is based on a talk I gave at BTTI 2022, and when I refer to all published ways, I want to be clear that most of them are my own. Every month, the BIPM publishes a circular T, which gives the difference between the time of each lab and UTC. This first row is for AOS, laboratory in Poland, and on the far right, it shows the uncertainty of these numbers. This column is a systematic uncertainty, and this paper is all about how to compute them. In 2020, three highly respected and brilliant members of the BIPM staff published a paper for the systematic uncertainties. In this paper, they made an assumption that the unknown bias of a lab's GNSS calibration equaled the bias of its UTC realization. Put that into a least square solution, and they found for a single GNS network that the uncertainty of lab K's calibration equaled the uncertainty of its UTC realization. Wildly different from what was before. One thing my paper points out is that least squares doesn't always work. In this highly simplified example that's easily generalized, there is a pivot lab connected to one lab by GPS and connected to another lab by Galileo. So there are 4 GNSS uncertainties that have to map into 3 UTC-K. Least squares can't tell you how to do it because you have to know which came first. I'm going to skip all the formulas to get to the conclusions. While the original way is self-consistent, it assumes the clock predictions are calcified, and there's some justification for that. But I think the PPH way is better. It has a few problems that I think this paper has fixed. Some other conclusions of the paper are that since the calibration uncertainties are assumed to increase with time, the cancellation is not complete, and you need to RSS the formulas of this paper with the original way. And there are other conclusions, but my time is up.